we're going to cover completing the square. Before completing the square, we're going to talk about the square root property. Let's say I have x squared equals 4. And our goal is to find solutions to this equation. What this equation is asking you to find is what number squared equals 4. Well, you may be able to think of one. If I square 2, that will equal 4. But if I also square negative 2, that will equal 4. Because when we square something, we're multiplying it by itself, and negative 2 times negative 2 creates that positive 4. So that brings up the square root property. It says if you have x squared, it equals some value a, where a is a positive number, then the solutions to that equation should be x equals plus or minus whatever the square root of a is. So going back to the example above, our solutions to this equation were x equaled 2, that was a possibility, or x equaled negative 2. And how is 2 related to 4? Well, it's the square root. So it turns out that plus or minus the square root of 4 gives me that plus or minus 2. Now it's important to recognize that that is what this plus minus serves as. It tells you that there are two solutions here. We have x equals the positive square root of a, but also x equaling the negative square root of a should be a solution based on this property. Let's look at an example of how we can use this to solve quadratic equations. Let's say that I have 3x squared minus 4 equals 68. We know that quadratic equations come in two forms. We either have a standard form equation, which looks like ax squared plus bx plus c, or we have a vertex form equation. When we have an equation in vertex form, we can just solve the equation or find its roots or find its zeros by just isolating x using inverse operations. I don't need any special techniques. I have all the techniques that we learned in an earlier algebra class, say algebra 1, where I can just move things to the other side to get x isolated. So for example, in this general form, vertex, I can move k to the other side by subtracting. I can divide by a to get rid of a squared. We're going to take the inverse operation, which is the square root. Now, when you take the square root in solving a quadratic equation, we must remember that we have to consider the positive or negative version of that square root in our solution. That is what that square root property was telling us, and we saw an example of why we must consider that. So I want you to remember and pay attention to, anytime you're taking the square root of both sides to isolate an x variable, remember to put a plus minus in front of that square root. It cancels out on the right side, so we just have x minus h, and then we can add h so that we have h plus or minus the square root negative k over a. So we were able to isolate x when it's in vertex form by just using basic inverse operations. The key thing to look at is when we take the square root to undo the square term, remember to put that plus minus in. But what do we do if we have a standard form equation? We can directly solve for x as long as the linear term is non-existent. So this is our linear term, and just to define, when we have the square term, that's our quadratic term. This is our linear term. And this is our constant term. So when the linear term does not exist, we can solve directly for x. So let's make a note of that. No linear term, solve directly for x. So we have that example off to the left. And you'll notice on the left side of that equation, we have a quadratic in standard form where that linear term is non-existent. So we can just solve directly for x. And there is no linear term on the other side of the equation. We should note that, okay? So as long as there's no linear term in existence on either side, then we're good to just solve directly for x. The way we do that is by using inverse operations. So we're going to add 4 to both sides. And we're going to divide by 3. 72 divided by 3 gets me 24. Next, I'm going to take the square root of both sides to undo that squared term. When we do that, anytime we take the square root, that square root property tells me I need to consider both the positive and negative root as answers. So I need to include a plus minus in front. So our answer is plus or minus the square root of 24. At this point, we would want to look at what's underneath the radical and determine, well, is that a perfect square? Can I simplify that? 24 is not a perfect square, but we can still simplify the radical. To simplify the radical, you want to determine what is the largest perfect square that evenly goes into 24. And you would determine that that is 4. So we can rewrite that square root as 4 times 6, because 4 is the largest perfect square that goes into 24. Then our radical properties tell us that I could break this into the square root of 4 times the square root of 6. And what's the square root of 4 but 2? So we were able to simplify the radical 24 into plus or minus 2 square root of 6. So if they ask you to simplify a radical, think, what is the largest perfect square that goes into that number? Break it up into a factorization of the perfect square times whatever it would take to get to that number. You can split the radical into 2 parts, and then take the square root of that perfect square that you consider. And that will get you your final result. So let's look at one more example to make sure we hammer this home. We have this quadratic equation. My goal is to solve this equation. Before, when we only had factoring at our disposal, we would have to set this equation equal to 0. But we're going to notice now that there's no linear term at anywhere in this equation. So there's nothing stopping me from solving directly for x. So we're going to isolate x using our basic inverse operations. If I add 20 to both sides, I get 25. If I divide by 4, I get 25 over 4. Then I can take the square root of both sides. Square root property tells me I need to consider the plus or minus. Now at this point, we're going to want to simplify. When I have it in fraction form, I can split it up. This is a legal move. And what that does for me is I have the square root of 25 and the square root of 4, which are both perfect squares, 5 over 2. And there's your answer. So remember that plus minus means there are 2 solutions there. We have x equals 5 halves, and we have x equals negative 5 halves. So now that we've established the square root property and how we can use it to solve quadratic equations, we're going to now jump into the main focus of this video, which is completing the square. So completing the square will serve 2 purposes for us. So its uses. 1, to solve equations, so to solve quadratics. And the nice thing about completing the square is we can always use it. So we mentioned before that factoring will not always be applicable to certain quadratics, but we can always complete the square. So solve quadratics, we're going to make a note that it's always an option. Its other purpose will be to convert from standard form to vertex form. So what we're going to do is we're going to look at what the process of completing the square is. Then we'll look at examples for each of these uses. So when we're completing the square, so the process, I'll go through the step-by-step process, and then at the end I'll actually show you a geometric interpretation why it's called completing the square. So the first thing you want to do is, again, we're going to be dealing with standard form equations. call standard form quadratics. Step 1. If a is not equal to 1, divide both sides by a. Actually, let's do that as the second step. Let's say our first step is actually, let's separate the variable terms and the constant term. So we're going to say variable terms and constant terms on opposite sides of the equal sign. So we'll do that as our first step. So we're going to get our variable terms on one side, constant terms on the other side of that equal sign. Step 2, now, if a is not equal to 1, so in our standard form is that a value is not equal to 1, then we need to divide both sides by a. The reason we do this is because we want a to be equal to 1. You need a to be equal to 1 in order to complete the square. So at this point, let's say we started so step 1. We got our variable terms on one side and our constant term on the other. From here, if a is not equal to 1, you need to divide both sides by a. So step 2, you're going to divide both sides by a so that a is equal to 1. So when we divide both sides by a divided by a gets you 1, and we now have an a value of 1. You're going to have plus bax equals c over a. Now, so we don't have to deal with these fractions. Let's just rename b over a. We're going to call capital B for that whole thing, and c over a we're going to call capital C. So now we're at the point where we have an a value equal to 1. Our next step is going to be to completing the square process. What you do is you're going to add b over 2 squared to both sides. So notice how I wrote the capital B. So whatever the new number is after you've divided by a, that's the new number you want to use for this third step. So we're going to add b over 2 squared to both sides. So step 3, what it would look like is going to be plus bx plus b over 2 squared plus c, equals c, plus b over 2 squared. That part, that plus b over 2 squared, this is the completing the square part. Now what that does for us is, on the left side, we're going to factor. And what you have is a perfect square trinomial every time, assuming you did this process right up to this point. And what the perfect square trinomial means is that you should get a duplicate factor pair. Meaning when you factor it, your parentheses should be the same thing copied over. And what it should factor into is actually x plus, and then the number you should get is whatever b over 2 was. That's the shortcut, actually. And because it's a duplicate factor pair where you're going to get the same thing twice, we can condense this into 1 by writing it as x plus b over 2 all squared. Now on the right side, you're going to want to combine whatever this value is. So if we combine those two things, let's call that full value d. Okay, so d just means the combination of this. So we'll make a note, d is equal to c plus b over 2, sure that's sloppy. So d is equal to c plus b 2 squared. Like up before, we'll just make a note, b is equal to whatever b over a was, and c is equal to whatever c over a was. Okay, so we started using capital letters. We're just doing this to condense everything and not make everything look so confusing. Now, what did we do? We took a standard form equation that had a linear term, and we removed that linear term. So now we can just use our square root property and solve directly for x. So at this point, so this is our factorization step. So let's highlight that step. What that factorization step did is it allows us to now solve directly for x. And this is why we discussed the square root property before. Okay, so there's no more linear term. I can solve directly for x. So at this point, we're going to take the square root. Actually, I'll just say solve directly for x. And once we've done that, we've got our solution. So how do we solve directly for x in step 5? We take the square root of both sides to start. Now remember, when we take the square root of both sides, square root property says we have to consider the positive or negative square root when solving that quadratic. So it cancels out on the left side, and all we're left with is x plus b over 2 equals plus or minus the square root of d. And remember, d was that whole thing that we just condensed down before. And then I can just subtract b over 2 to the other side and get plus or minus. Now remember, b and d, they just represent some number. So we're going to get some value here, and that's our solution. And there are two solutions there because of that plus minus. So that is completing the square process. Now, what is the geometric interpretation of this? Well, once we've gotten a value of 1, and we got to the point where we have x squared plus bx, okay, that completing the square, we said, was that adding the b over 2 squared part to both sides. So I mentioned that was the completing the square part. So where does that come from, and what does that mean geometrically? What we can do is we can look at that x squared as an area formula for a square, where the side lengths are x and x. Okay? Where that area inside is x squared. Now what we can do is look at bx as a rectangle, where its vertical length is x, should match that square, and the width is b. What we can do is split that rectangle into two parts, where this is now b over 2 and b over 2. We cut it right in half. And I can take each rectangle that I've just made, these sub-rectangles, if I attach it on to the side of the square, so I split the original rectangle that was a b by x into a b over 2 by x. So each part, we have b over 2, and b over 2 as the new width when I split it in half. The lengths are still x. You'll notice there's a piece missing in the bottom. And adding in that piece, that is the completing the square. We are literally completing a square, hence the name. The question is, what was the add in to complete it? Well, what are the dimensions of that little square there? Well, if you notice the other parts, you'll see that the width and length of that little square should match b over 2 and b over 2. So the dimensions, it's b over 2 times b over 2. So to complete the full square, we have to add on b over 2 squared. And that's where that comes from. That's where the plus b over 2 squared comes from. Now the factorization, we can see that the area of this fully new square, we have x squared plus, then one rectangle is b over 2x plus the area of the other rectangle is b over 2x plus that new little square that we added on to complete the square, b over 2 squared. We know that should equal the length times the width, which can also be written as x plus b over 2, x plus b over 2. And knowing how to calculate the area of a square, we just do the side length squared. So an alternative representation of our newly formed square, its side length can be represented as x plus b over 2. So we could say that the area of that new square could also be expressed in the following way. These are equivalent statements. So if I combine the like terms over here, half of b plus half of b equals 1 of b. When I have two things multiplied together the same thing, I can condense it down. So we said, once we get to this point in the above process, we can factor it, and what we should create is a duplicate factor pair, a perfect square trinomial. And as evidenced by this geometric interpretation, we can see that we should get a duplicate factor pairing. So there's a geometric support of completing the square, and why is called completing the square. Now let's look at two examples. Actually, let's look at the two uses, I should say. So example 1, we're going to do a solving problem. So we're going to solve. Two x squared plus 8x equals 12. The first thing you want to do with completing the square is make sure your variable terms are on one side and your constant terms are on the other. That is already taken care of for me. The next thing you want to do is make sure your a value is equal to 1. So in order to do that, we must divide both sides by a. So I need to divide both sides by 2. When I divide both sides by 2, we're going to get x squared plus 4x equals 6. At this point, we're ready to complete the square. We must add b over 2 squared to both sides. Now, I don't want to use the original b. We're using this new b term here, okay? So when I go in to actually complete the square process, we're adding 4 over 2 squared to both sides. Okay, important, because what we do to one side, we must do to the other to maintain symmetry in the equation. Once I've done that, you can simplify that if you'd like. So 4 over 2 is 2, 2 squared is 4. Factoring the left side. We already know we should get a duplicate factor pair, but what I'm asking myself is what multiplies the 4, adds the positive 4. That's positive 2 and positive 2. We see that we got a duplicate pairing, so I can express it as x plus 2 all squared. The reason I would want to express it as that thing squared is because now I can directly solve for x by taking the square root of both sides. That is the inverse operation of that squared term. But remember, when we take the square root of both sides, the square root property tells us to consider both the positive and negative root. Then lastly, I can subtract 2. So we're going to get x equals negative 2 plus or minus the square root of 10. I'm going to look to see, is the square root of 10 a perfect square? It is not. Can I simplify it any further? Unfortunately, there are no perfect squares that are go evenly into 10, so that's the best I can do, and that is my final answer. There are two answers there. Keep in mind, we have negative 2 plus the square root of 10, and we have negative 2 minus the square root of 10. Okay, but that is the completing the square process. Keep in mind that separate variables and constants. It's important that you have an a value equal to 1. You cannot complete the square unless that is taken care of first. And when we add b over 2 squared to both sides, you're considering the b term after you've made a equal to 1. Get it? So let's add that into this process. So when we add this b over 2 squared to both sides, that's step 3. This is after you've made a equal to 1. Okay? So that is how we can use completing the square to solve an equation. Now, how do we use completing the square to reformat? So we're going to say standard to vertex. We know standard form, what it looks like. Let's get a reminder of vertex form again. We want something that looks like this. That's what we're trying to produce. So let's look at an example. If we start with some function f of x where it equals x squared plus 24x plus 145. That is a standard form equation. We want to convert it into a vertex form equation. This would be slightly trickier than when we're just solving, but it's the same idea. Separate your variable terms and your constant terms. Now, I'm going to consider f of x as a constant term in a problem like this. So I'm going to move 145 to the other side. We want to make sure our a value is equal to 1. Luckily, our a value is equal to 1 here. If it wasn't, we would divide both sides by a. At this point, we are now ready to complete the square. So we are going to add b over 2 squared to both sides. So our b term is 24. So 24 divided by 2 is 12. 12 squared is 144. Okay, so if you have to do that work off to the side, we're going to do 24 over 2 squared is equal to 12 squared is equal to 144. So what I add to one side, I must add to the other side. So let's actually do that in a new line. That'd be better. So we've added our b over 2 squared to both sides. Now let's simplify this left side. So we have f of x equals, now it's going to be, f of x minus 1 equals, now again, once we've completed the square, this should be a perfect square trinomial in the sense that when I factor it, I get a duplicate factor pairing. So what multiplies to 144 adds to 24? Positive 12, positive 12. That's good. It's a good thing that I'm getting that duplicate factor pair. That needs to happen. We're going to write it as something squared. And then I'm just going to resolve for f by moving that constant term back over. Now you'll notice that this is now in vertex form. And now I can easily identify the vertex. In fact, the vertex in this case is negative 12, 1. Because it went left 12, up 1. So we can take a standard form equation and use completing the square to convert it into a vertex form equation. Now I'm going to end the video on one additional example relating to reformatting, where if you do have an a value greater than 1, so you can see how to handle that. So if we have f of x equals 5x squared minus 50x plus 128. First step, let's get our variables on one side, constants on the other. So we're going to move that 128 to the left side. Now you'll notice we have an a value greater than 1, so we're going to divide by 5. Okay, we're going to divide both sides by 5. So that I do have an a value of 1. Now I can't simplify that left side, so you're going to have to get used to the fact that we're going to keep it kind of in that format that it's currently in. And it's going to be okay at the end, as long as you follow what I'm writing. So we're going to leave it over 5 like that, because I can't simplify anything. The right side I can't simplify. We're going to get x squared minus 10x. Now I'm ready to complete the square. Again, to complete the square, you're going to use the new b term after you've made a equal to 1. So off to the side, we're going to add b over 2 squared to both sides. So b over 2 is negative 5. Negative 5 squared is a positive 25. So we're going to add 25 to both sides. So again, that plus 25, that's the actual completing the square process. On the right side, once we've completed the square, we should get a duplicate factor pairing when we factor it. What multiplies to 25 adds to negative 10. You should get x minus 5, x minus 5. That duplicate factor pair is what we want. We can write it as x minus 5 squared. On the left side, we still have this mess. But now we can resolve for f of x to get that vertex form that we're looking for. To do that, the first thing you're going to do is subtract 25. So make sure you do the correct order of operations. Then we're going to multiply both sides by 5. When we multiply this right side by 5, notice what happens here. This 5 is going to go in front of that parenthesis, and then this 5 also has to multiply this negative 25. So that's a common mistake that I've seen in the past. Make sure it's distributed to both things. We're multiplying the entire side by 5, so it has to distribute in. So what we're going to get here is 5, x minus 5 squared, minus 125. Okay, so that 5 has to distribute to all terms on the right side. Then lastly, we can add 128. So we have 5, x minus 5 squared, and then when I add 128, we're going to get plus 3. And that answer is in vertex form, where we can see that the vertex is at 5, 3. So it went right 5, up 3. So that, again, is how you can use vertex form, or sorry, completing the square to get a vertex form equation from a standard form equation, and that is an example of how you use, or when faced with an a value that is not equal to 1.